Right, so example 2 of 4.5 and 4.6a is going through the complex conjugates theorem. So, complex conjugates theorem tells you, all of us, if there's a polynomial function and it has an imaginary zero of a plus bi, it must also have an imaginary zero at a minus bi. Again, because of when you reduce down that quadratic equation all the way down using your quadratic formula, you might get something like a plus or minus bi, so we're representing both of the zeros that it's giving us. So if you need to write a polynomial of least degree with rational coefficients, a leading coefficient of 1 and zeros at 2 and 3 plus I. So we're going to use the process that I used on the irrational conjugates theorem, but we're going to apply it to the complex conjugates theorem. So step 1, you're going to list out your zeros. So you're given zeros at 2 and 3 plus I. So these are values that if you substitute them into the function, they would cause an output of 0. If you put the function on a graph, they would be where y equals 0, so they would be your x-intercepts. So the complex conjugates theorem tells us that if you have a 0 at 3 plus I, then you also have another 0 at 3 minus I. When you have zeros and you need to write out a polynomial function, you need to take those zeros and create the factors. So they're in that x minus h style. So when I have a 0 at 2, then I have x minus 2. Because if I put 2 in for that x, I'd have 2 minus 2, and it would become 0. Right, so they need to be zeros. All right, if I have 3 plus I, then I have x minus 3 plus I. I'm using brackets because those pieces need to stay together. And if I have 3 minus I, then I have x minus 3 minus I. Those two can simplify. So this is 3 minus, x minus 3 minus I if I distribute that. And if I distribute and simplify this, I have x minus 3 plus I. Still following that conjugates theorem. If I subtract an imaginary, I must also add that imaginary. If I have an imaginary adding, I must also have one subtracting in the same term. So, zeros, look at what you have, decide if there's an unwritten one based on a conjugates theorem, take those zeros, turn them into factors. Use those factors to write the factored form of your polynomial. Right? So this represents a function. We have x's, and it would give us outputs. Factored form, I'm going to take those 3 factors and multiply them. So x minus 2 times x minus 3 minus I times x minus 3 plus I. This I does not represent just a random piece of information. It is not a random variable. It actually has a set value to it. So just as a reminder, when you have I squared, you can replace that with the value of -1. If you ever have the square root of -1 or any negative number, it can be replaced by a value of I. So on the left side, that I squared and the square root of -1, okay, those are not considered rationalized or simplified. You would need to convert them either to a -1 or to an I. So these terms on the right here are what we are allowed to and need to replace in order to finish out any function we have. So we need to keep that awareness as we do this problem. Right, so When you have it in factored form and you have complex numbers or the imaginary I, you want to distribute those factors first. It will simplify the fastest. So we're going to keep our x minus 2. We're going to deal with that at the end. And we are going to distribute your two complex factors. So x times x is x squared. X times negative 3 is negative 3x. X times positive I is plus xi. I'm going to use that negative 3 now and distribute that. So negative 3 times x is negative 3x. Negative 3 times negative 3 is a positive 9, and a negative 3 times I is minus 3i. Then I need to use that negative I. This one we have to be careful of because of what I represents. So we have I times negative x, so negative xi. Negative I times negative 3, so positive 3i. And then negative I times a positive I, so we have negative I squared. So we need to begin to simplify those. Alright, so when you use the complex conjugates theorems, the reason that we distribute the two complex factors first is it will simplify out every complex term. Right, so it gets really long, what we have now. Now we're going to shorten it down. So that complex conjugates theorem says if you have a positive imaginary, you also have a negative imaginary. We should see that pattern and they should zero each other out. So I see here a positive xi and a negative xi. Those zero each other out. I see a negative 3i and a positive 3i. Those zero each other out. And I see a negative I squared. What does that represent? Oh, well that represents negative of negative 1. Okay, so I need to think of that. So we still have our x minus 2. We have not distributed that at all. And let's see what we have left. We have an x squared. We have negative 6x's. And we have that positive 9. And what is negative of negative 1? It's a positive 1. So negative 9, or sorry, positive 9 plus 1 gets me a 10. So we began simplifying. Like I said, they get really long, then they get really short. We still have two factors, so we need to distribute those. So let's begin that process. X times x squared is x cubed. X times negative 6x is negative 6x squared. X times 10, positive 10x. I'm going to take that negative 2 now, times x squared, so minus 2x squared. Negative 2 times negative 6x, so plus 12x. Negative 2 times a positive 10, so minus 20. I have one set now, but I do need to simplify it down. Alright, so highest term, x cubed. Next terms, I have x squared, so I have minus 8x squared. My next term is my x's, so plus 22x. And then my last value of negative 20. Let's see, is it a polynomial? Yes. Is it a least degree, standard form, 3, 2, 1, 0? Yes. Rational coefficients, leading coefficient of 1, so that's from our instructions. Yes, there's only one x cubed in the front here, and I utilized all of my zeros. Alright, so we're going to do another one. I'm going to do this one slower. I'm going to take pauses. I want you to do this one on a piece of paper so that you can try this out on your own. Alright.